Thank you very much to the organizers for giving me this opportunity. I'm Dr. Salvatore Sessa from the University of Naples, and I will present something about parameter identification, thermodynamic compatibility, and if we have time, some random vibrations analysis concerning an hysteretic model that was presented to the Italian audience this morning by Dr. Vaiana, and I believe that the video will be made available after the event. Actually, we discuss some features of a single uniaxial constitutive model that belongs to a wider phenomenological class. It is one of the symmetric hysteretic materials. And this is a very schematic outline, because we will start with parameter identification, and then I will make some insight on thermodynamic compatibility of this model, and if we have time, also an application concerning a random vibration analysis that we made with this model. So let's start with the identification that we published in this paper for the details, and just a brief overview of the material that I am considering was the one that was called the algebraic material, and I will address it hysteretic poly just because it was implemented into a finite element framework, and this is the official name that it has been used. Actually, this one is implemented in OpenSys, and it is a non-iterative model, since it is capable to compute the structural response, uniaxial response of the material in closed form without requiring any iteration. And we can reproduce a different kind of hysteresis, different shapes, by means of just 5 constitutive parameters. These are a few equations just to fix the ideas. And actually, U0 and F are 2 auxiliary parameters depending on these 5 constitutive ones, Ka, Kb, alpha, and beta 1 and beta 2. Actually, this is a kind of the hysteresis that we can get. And this is everything that we need to compute the response. There is the force, which has pretty complicated formulation, but it is a closed form solution. And actually there is this variable, which is kind of history or internal variable that deals with some permanent deformation of the material. Actually, these are some shapes that we can get, and this is important to recall the physical meaning of some of the parameters, because A is at the beginning of the loop, while Kb is the stiffness at infinite, or if we, or also at the center at the zero displacement of the external curves, while alpha alpha rules the transition phase between 2 boundary curves that are the top and the bottom boundary functions, while the latter quantities, beta 1 and beta 2, are used to provide some kind of nonlinear behavior in the hardening or softening phase. These are 6 numerical examples, but also we have some interesting hysteretic loops calibrated on experimental data, and this is the goal of this first part of the presentation, just to take the data and get the parameters. So we often stress about kind of similarity between our models and the book when, And this is because besides the fact that the two formulations are completely different from a mathematical point of view, actually they provide shapes of the hysteresis which are quite similar, and actually they have some common properties, such as the fact that they are smooth and that can implement pinching, hardening, softening, and so, and even local minimum and maximum. Actually, when we deal with the book one formulation, which is defined by means of the derivative of a nonlinear deformation, then this means that identification of the parameters can be quite difficult, because there is no an inverse relationship between the response and the parameters. In fact, actually, the calibration of Bookwen models frequently requires heuristic approaches, such as artificial intelligence or genetic algorithms or similar, that can be not quite easy to perform for practitioners. On the contrary, the identification of this model can be performed by a simple iterative optimization because of the physical meaning of the parameters. Actually, the identification procedure consists in three subsequent steps. The first one is a pre-processing of the experimental data. And then there is a first identification, let's say a preliminary identification, which is focused only on a subset of the parameters. And then a refinement identification that is needed to identify, to enhance the estimate of the parameters, especially for the two remaining ones. Actually, the pre-processing phase is quite standard, because we get the experimental data, such as this one, which was probably an elastomagnetic damper. And we split all the branches of the loop. Each branch is identified separately. Actually, we also cut the tip at the end, because this is a well-known phenomenon that is related to the inertial contribution of the experimental device. And actually, this can affect the stiffness at the end of the tips. So it's better to neglect this part. And actually, after that, we start with the proper identification. Actually, for each generic branch is defined by means of a set of discrete set of displacement and associated responses. For each one, we first split the parameters in two different sets. The first set is Ka, Kb, and alpha, and we collect it into this vector. While the second one are the two beta, we collect them into a second vector. And we set a least square residual by means of the difference between a relative difference between the theoretical response, which is this one, Fe, and the experimental response, Fe, and the computational one that we get, and depends on the specific set of parameters. Actually, this is a kind of standard deviation of the gap between the curves. The identification can be summarized by just an optimization procedure depending on the parameter, and is the same both for the first one, the preliminary one, and for the refinement identification. Actually, despite of its formal simplicity, there are some drawbacks from a numerical point of view, and we need some expedients to get convergence of the algorithm, because the robustness of the optimization algorithm is strongly influenced by especially the initial trials of the parameters, but also is influenced by the sensitivity of the response with respect to the parameters and on the number itself of the parameters that we consider within the algorithm. So to improve robustness and convergence of the identification, we perform the preliminary one, which is focused only on 3 parameters, and the second one that includes also the latter 2. This figure represents a generic theoretical transition curve of the hysteretic model, in which we can see some parameters reported on the graph. And actually, if we wish to get an appealing, a consistent first trials for the parameters, the easiest way to do it is to compute the tangent stiffness at the beginning of the branch for Ka and the tangent stiffness at u equal to 0 for the Kb case. For what concerns alpha, alpha has not a direct physical meaning. I mean that I cannot see it in the graph, but actually this is related to this other quantity, u0. And actually u0 is the displacement interval that brings my response from the transition curve. This point actually is supposed to be on the bottom part of the hysteresis loop to the top boundary of the hysteresis loop. Actually, we got that numerically, a good estimate for this quantity is to assume that this displacement interval is equal to the largest amplitude of the branch, so that if we fix that 2u0 is equal to delta, which is this distance, then we can invert this relationship here and get the first estimate of alpha. Of course, this one is actually, this quantity is overestimated, but actually this provided a good convergence of the algorithm. After that, then we are able to perform the first preliminary optimization procedure so that we get at convergence a set of 5 parameters. Actually, these 2 are considered by the algorithm, but these are fixed to 0 at the beginning as first trials, and they don't really move from their first trial. So the first identification is not really sensitive to the beta parameters, but actually, in some cases, this first step is already sufficient to provide a good accuracy of the hysteretic model. And this happens when we have a kind of linear hardening behavior at the end of the curve. On the contrary, sometimes it is necessary to perform a better estimation also for the 2 remaining parameters. And so we need the refinement optimization procedure. And so we need to evaluate, to estimate a new first trials for the optimization algorithm. In this case, as a first trial, we set for the first 3 parameters just the result of the preliminary identification, while the new trials of beta are computed as function of the first 3 parameters. This is because actually beta 1 and beta 2 are needed to introduce in the boundary curves some kind of behavior like these ones. So for example, they are used to introduce local maxima or minima, or to adulterate the stiffness at the tip of the hysteretic loop. So we can set two, let's say, hot points of the graph. If we have a local minimum or maximum, then this one is a good candidate, as well as the point at the end of the loop. If we don't have maximum, then we just take the stiffness at the point that is at half of the maximum displacement. And so we get two experimental values of the stiffness, so that if we take the closed form function of the theoretical stiffness of the material, we can invert it. Actually, this can be done in closed form because this one is the first part of the stiffness. No, actually, this is the tangent stiffness, generic tangent stiffness. So if we invert, if we set two equations so that my theoretical stiffness must be equal to the experimental ones, then we can get this system which can be inverted, and so that the first trials of beta can be computed in closed form. And actually these ones are introduced into an optimization algorithm again, and we can get the final estimate of the parameters. Actually, these two are two pseudo-experimental tests, and actually, if we just try to identify the real response of the material, we get a perfect convergence. Actually, the error is zero. It's not even a numerical zero. It's just the algorithm provides the right numbers. While in case of experimental data, then we have some discrepancy, but actually it's a very good approximation of the experimental response. Actually, in this figure, we see the experimental curve in blue, while the green one is the result of the first of the preliminary optimization. And actually, we can see that while the stiffnesses here and at this point here are matching the experimental ones, we completely lose the hardening effect of the loop, while the refined identification, which is the red curve, matches the experimental one. Actually, this is a second experimental value, and in this case, we also have non-monotonic stiffness in this region of the loop. And this one is also another, this was the wire rope isolator of, it's a wire rope isolator loaded by transverse load. And this is the same wire rope, but the load should be longitudinal. Actually, this material was implemented in OpenSeas, and it's freely available because the framework, the finite element framework, it's open source. And also, actually, this is the syntax for the creation of the material. And actually, we also implemented a freeware for the identification by experimental data. And if I found it, then I would like to show just a simple example. Actually, this one is the freeware. There's Excel. Yeah, it was shared the screen. So actually, these are experimental data, and I just paste it here. So here we get the experimental loop, And here, this figure represents what we are identifying. So we cut the tips, and then we can run the identification. So one important thing is that here we get the results, and actually we have different parameters for each branch of the loop. And actually the ones that we usually take for computations are just the averages of the ones relevant to the branches. Actually, there are some exporting functions for OpenSys, but I think that they're trivial. And one important thing that it introduced, the second part of the presentation, is this one, because here it is represented a displacement range for the thermodynamic consistency of the material. Actually, this range is reported here. So let's go to the second part of the presentation, and let's deal with some thermodynamics. Where's the presentation? Ah, thank you. Okay, so let's deal with thermodynamic compatibility. Actually, thermodynamic compatibility for phenomenological model, because this model is not yet variational, consists in the Drucker's postulate that actually states that the increment of inelastic work, that is the dissipated energy, must be non-negative. And making reference to the case of plasticity, just to fix ideas, this means that the scalar product between the stress rate and the plastic strain rate must be non-negative. Actually, this is not trivial for such kind of phenomenological model, because we can find some strange behaviors. And so to investigate this, we fix some work quantities. We will compute a total work while the response is computed, a kind of elastic work. I will call it elastic just for analogy with the classical theory, but actually this is not an elastic behavior, but this is the work that is associated with the unloading, a generic unloading of the material, and the inelastic work, which is the one dissipated by the material, that is the difference between the first two terms. Actually, in order to fulfill the Drucker's postulate, we must enforce this condition. We must actually verify this condition. This is not always satisfied by phenomenological materials, because it is not trivial that this quantity is non-negative. Actually, this figure represents the elastic work, the one that I called elastic, and is associated with the generic stress-strain equilibrium state. Actually, stress-strain or load displacement is the same thing. Actually, one reason for a non-consistent material may be the fact that the curve goes behind the horizontal axis, so that positive increments provide a negative work, negative total work. But also the fact that if I have an irregular behavior of the material, for example, a seismic action, and actually I have a lot of vibrations, then I may have a loading curve that intersects the loading one, so that in this case, the total work, which is this blue area, is less than the elastic work associated with this equilibrium point. And so in this case, the inelastic work would be non-positive. So we have to check if for our parameters, what conditions I can enforce on the parameters in order to ensure the compatibility. In case of negative strain increment, this is trivial, because if we pass from this equilibrium to this one, then it happens that some part of the elastic work is released by the system, and so trivially the inelastic work, the increment of inelastic work is 0. But actually, if I have positive rates of the strain, then things are a little bit more complicated, because I have to estimate this area by introducing a little increment of the strain. And actually, this increment of total work may be computed by a second-order Taylor expansion, so that we have, actually, this is a first-order Taylor expansion. We have the derivative of the stress with respect to the strain times the strain square. While the increment of inelastic work is computed by means of the increment of elastic part. So the elastic increment is this green area here at the bottom. Here is magnified figure. Actually, this is because a typical feature of this class of material. And actually, it is because the transition curve, this red curve, actually translates if we start from another point of the boundary curve. So we can estimate the green area by considering this height here of the trapezoidal area. And actually, this is just a derivative exercise, but we can get these two quantities as a linearized as function of the linearized stress-strain relationship. And in this case, we have the increment of elastic work so that we can make the difference. I'm not providing actually all the analytical part, because this is the generical difference, but this must be specialized for all the combination of parameters. But just I say that we neglect some terms here because these are infinitesimal quantity of higher order. And actually what happens, just 5 minutes, is that let's go at the end. Actually, we get this condition here for which a general purpose conservative condition about the thermodynamic compatibility of the material consists in checking that the minimum of the second stiffness over the maximum of the tangent stiffness is greater than 0.5. If this condition holds, then the material is compatible for any equilibrium, for any possible equilibrium state. Actually, this is not true for several cases of parameters, for several combinations of parameters. So if this is not fulfilled, then we are capable to get a compatibility range of the material that is an interval of strain or displacements for which the thermodynamic compatibility is fulfilled. And actually, we tested conditions over with 7 different constitutive model. Actually, here we tried to switch the algebraic signs of these 2 parameters that affect the compatibility range. Actually, the compatibility range may be often computed in closed form depending on the combination of the signs. And actually, these are the outcomes. Here, there are the loops. These are quasi-static tests. And on the right, we have the total work, which is the solid line, and the dashed one is the inelastic work. While these two vertical lines represent the compatibility range. Actually, we got compatibility conditions also for displacement that are outside this range. This is because the condition that we get, the analytical condition about the stiffnesses, it's quite conservative. So it is not, it may be not true that if we go outside, then the material is not compatible. And there are some future examples like this one. This one is more tricky. Actually, here there is the unloading curve that it is not definitely not elastic, and also this one. But the most interesting ones are the two seismic tests. These are two dynamic tests performed on parameters calibrated on experimental data. And in this case, we have an evolution of the total work versus time. And actually, this is not monotonic, but the inelastic work, while we are inside the compatibility range, is non-decreasing. So we don't have time for the third part. I just say that we used this material because of its capability of providing the response in closed form, so it does not require iteration, also in random vibrations analysis. But I hope I may present it in the future. And I will provide some conclusions. So actually, I already said that because closed form solution, it's very effective from a computational point of view because it's fast. The identification, because of the possibility of getting effective first estimate, it's quite straightforward and maybe performed even by people that don't have confidence with identification, and is thermodynamically compatible as far as we remain inside the boundary. As these were related to the random vibration analysis, actually, as a future work, we will extend identification and compatibility to the asymmetric hysteresis and to multidimensional responses, but also a couple of research direction deal with the gradation of the material, and also with design optimization of phase-isolated systems by means of the random vibration analysis. Actually, I have done, so I thank you very much for your attention.
First, I ask if in Peru there are questions. Francisco, are there questions from Peru?
No, no, Emilio.
So, yes, do we have questions, comments? So I have one question. So my question is, so you have a kind of sufficient condition for a thermodynamical consistency.
Yeah.
I say sufficient because even it is not necessary, because even when it is not fulfilled, then you could have thermodynamical consistency. So my question is, this is basically a kind of bound, I think, that you find. This is the reason why it is sufficient. So how much sharp is this bound? So how often does it happen that that you have cycles which don't fulfill I mean, whose states don't fulfill, or at least regions of cycles who don't fulfill this inequality but are still thermodynamically consistent. And another issue is whether you think if it is possible to create a kind of software that can automatically tell you what are the regions which are thermodynamically consistent, so that you run your code and you see which are the regions which are admissible.
Well, actually, the reason about the conservative nature it is related to this one that I jumped for Rush, but actually we involved the second stiffness because we try to match a linear decreasing curve. Matching the red one. Actually, when we compute the minimum and the maximum of the stiffness, we do it because we don't know where in which part of the equilibrium region we may be. So this is both the minimum and the maximum are a kind of asymptotic conditions. And actually, in my experience, we were never capable of achieving non-compatibility for seismic cases. But the non-compatibility, the more frequent case was related to this behavior here. So if when we have softening, then it happens that the curve gets the axis and then we go out of the bound. Actually, I don't think that it is that frequent, but it was a check that we did because a question about compatibility of the material arises in some applications, and in comparing it with the Boquin material that for some cases, for some values of the parameter is not compatible as well. So actually this is a check that we made, and that is a kind of a preliminary to an hemivariational formulation of this class of materials, because the general considerations about stiffnesses may be applied to the whole class, while the values that I got and are reported in the paper are relevant just to the polynomial material.
Okay, thanks a lot, and thanks for the